Okay, in this problem we're going to look at the number of different combinations that are possible in a password. So part A, how many different passwords are possible? So let's read their rules for these. So it consists of 4 letters A through Z followed by a single digit. So 1, 2, 3, 4. So those are going to be letters, and then you get one number. Assume that the passwords aren't case sensitive. So why is that important? Well, if lowercase and uppercase are counted differently, then there's 52 different letters instead of 26, right? And so here it doesn't matter if they're upper or lowercase. So that means for each one of these, there's like 26 choices, right? For A through Z. How many different passwords are possible? Okay, so for your first letter, you could pick 26 different things. Next one, you could pick 26 different letters. You could use the same letter even if you want to, right? Then you could choose 26 different letters. So in all 4 of the letter slots, you have 26 choices, right? And then the digits 0 through 9, picture you have 10 choices then, because you have 1 through 9, or you could pick 0. So that's 10 different digits. So if I'm looking at how many possibilities is that, sometimes I'll throw up the graphing calculator here if I can. It looks like it's 26 times 26 times 26, right? 4 different letters times 10 different numbers. So 4, 5, 6, 9, 7, 6, 0. Put my commas in after. So looks like about 4.5 million choices if those are the rules for passwords. Okay, so then part B, they're going to let us pick other choices here. So how many different passwords end in a 1? All right, so you can still do whatever you want for the 4 letters. So your choice there is the same, right? You can pick 26 different letters times 26 different letters times 26 different letters, because you could pick a different one for each. And then if it has to end in a 1, that means you only have one choice for your last number. Not because the digit's 1, but because if they tell you, hey, it has to end in a 7, well then you only have one choice. You can only put a 7 instead of 10 different choices of numbers. So this is how many choices we have. So it looks like for that, that's 26 times 26 4 times. Maybe just to save a little bit of time, I'll use the exponent here. This button means the exponent, the little caret it's called. So 26 to the 4th times 1. And obviously multiplying by 1 doesn't do anything. So if you don't want to type that, you don't have to. Okay, so what did that do to our number of choices? 4, 5, 6, 9, 7, 6. We have 10 times less choices because instead of picking 10 different numbers here at the end, so instead of 4.5 million-ish, there's only 450,000 combinations of passwords. Okay, then part C. How many different passwords that do not start with a Z? All right, so if it can't start with a Z, that means you have one less choice for your first letter, right? So you only have 25 choices instead of 26. But then for the rest of the letters, can be anything. It just said it can't start with Z. So you still have 26 choices for all of these. And then you still have 10 choices for your numbers. The only stipulation in part C is that it can't start with a Z. And so that's what? 25 times 26 to the 3rd, because there's 3 of them. Just saves time in the typing. If I want to get out of the exponent, notice I hit the over arrow to get back in and out of it, because I need this times 10 otherwise to not be part of the exponent. So 25 times 26 3 times 10. So it looks like in that one it lowered it. If it can't start with a Z, it lowers it from 4.5 million choices to 4.3 million choices. So it didn't lower it as much as some of the other things. All right, then the very last one, how many different passwords have no Z's? Alright, so I can't pick a Z at all. So that means I only have 25 choices for my first letter. Now I only have 25 choices for my other letters too, because I've eliminated Z as a choice. And no stipulation on the number, so I still have 10 different number choices. So it looks like that comes out to 25 times itself 4 times. And then times, I have 10 different choices for numbers. And as you can imagine, it's less than the big number. It's also less than this one. So if we can't have Z in the first one, that takes out one choice. If you can't have Z at all, it takes one choice out of each of these. So it actually lowers it from 4.3 million to 3.9 million-ish.